Alrighty, so 222 part 2, just some more on slopes and lines, that kind of thing. So it says the slope of a line can represent many things. In this lesson, you concentrated on situations where the rate of change of a line, the slope, represented speed. However, rate of change can represent many other things besides speed, depending on the situation. So for each graph below, explain what real-world quantities the slope and y-intercept represent, and then calculate the unit rate for each situation. So on the first one, it looks like the slope would be it's going from 4 to 14. So my change in y is 10, and my change in x is 5. So 2. But 2 what? Well, it looks like the height of a tree over years of planting. So this thing is growing 2 feet every 1 year. And I already actually have it in unit rate. My y-intercept, or my starting point, would be 4. So my equation would be y equals 2x plus 4. And again, if I plug 0 in, I get 4. If I plug 2 in, if I plug 5 in, I get 14. So that equation seems to make sense. It says, in each of these situations, would it make sense to draw a different line with a negative y-intercept? I know people shrink as they get older, but I don't think trees do. So I would say that would not make sense. All right, let's look at this one. This one, our slope is down 20 and over 2. So my slope is going to be negative 20 over 2, which is negative 10, which means that I'm losing $10 a month in my bank balance. And my starting appears to be 170. So I started with $170 in my account, and I lose $10 a month. So my equation would look like this. And again, if I plug in 2, I expect to get 150, and I do. If I plug in 4, I expect to get 130, and I do. So it's a good idea to check your equations, make sure they're right. And would it make sense to have a different line? Yeah, I mean, you could easily have a balance go up instead of down. So I think that makes a lot of sense. And by the way, it says calculate the unit rate. I did calculate the unit rate. I'm losing $10 a month here. $10 every 1 month. Excuse me. Sorry, I had a big sneeze right there. All right, next one. You can see it's going up 44, and it's going over 2. So it's going up 44 miles, so every 2 gallons of gas. So my unit rate would be 22 miles for 1 gallon. My starting point is 0, so that's my M. My B is 0. So I don't go anywhere when I use no gas, but when I do, I use 22 miles a gallon. My equation would be 22x. By the way, that's a proportional relationship. If you remember, it starts at origin and it goes proportionally up. And would it make sense to have one go down? As you use gas, you not only, that's not even saying going backwards. It's saying going like negative distance. I don't think you can really go negative distance, so I would say no to that. All right, take a walk. The president of the Lion Factory is so impressed with your work that you have been given a special assignment to analyze the graph below, which was created when a customer walked in the front door of a motion detector. The motion detector recorded the distance between it and the customer. So we're going to ignore the resource page. It says the graph is a piecewise graph. A piecewise graph is a graph that has a different equation for different intervals. So what they're essentially saying is, at this point, the equation is y equals down 1 over 1, 2, 3, 4. So negative 1/4 x plus 5. The equation here is just y equals 4. And the equation here is y equals, 1, 2, 3, 4, 5 over 1, 2, 3. So 5/3 x. So if I go 1, 2, 3, and 1, 2, 3, I'll go down 10 more. So 4 minus 10 is minus 6. So I think this one, I'm not sure. I think that's the equation. The bottom line is we have 3 different equations for each different piece of the graph. By the way, domain becomes really important going back to chapter 1, right? So here we would say the domain is important between 0 and 4. Here we would say the domain is important between, we would say, I guess we could say 4. I won't use the equal sign because I already used the equal sign here. So between 4 and 6. And here we could say the domain is x is greater than 6. We jump over to this line. So again, the domain kind of breaks those pieces up. That's just sort of a side I throw in. I don't know why, but I hope that makes sense. So really we want to describe what's happening when we look at this motion detector. And if you think about it, what seems to be happening is this. Here the distance is going lower, but slowly. And then it stays the same, and then the distance gets greater fairly quickly. So to me, what it looks like is the customer walks in, he's kind of slowly walking in, maybe looking at the motion detector, kind of wondering what it is, kind of stops and stares at it for a couple seconds, and then turns and walks away. That's what it looks like to me. Oh, and good news, it did ask a lot about the domain and that kind of a thing. At this point, my notes have that I finished this lesson here, but I'm going to go ahead and pause the video and look to see what happens if I do want to go over some of the other stuff. Pause the video because I did want to talk about this one as well. So problem 256. It says, write a memo to the president of the line factory explaining why you cannot use a motion detector to collect the data plotted below. So look, on this one, time isn't passing, but the guy's moving. So somehow this man has managed to stop time but move, which doesn't make any sense. This one, you can see that the distance has like these jumps in them, right? So it's kind of weird. This guy's here, and then he's in 2 places at once. Right? Time is going. He doesn't walk between one and the other. He just sort of appears, and he's in both at once. Then he's only in this spot. Then he's in both of these spots at the same time. So this guy has managed to teleport, and this guy's managed to stop time. So again, that just doesn't really make a lot of sense as far as that goes. So anyway, learning log, math notes if you're so inclined.